Just let me know.
Yes, we see.
Great. Okay, so I'll start in a second. Good. So thank you for the invite. Happy to be here and talk to you about our work on automation of AI. So what today I'm going to present to you is a summary of our work on, particularly focus on a tool that we call NeoNet. NeoNet stands for Neural Network Architecture Search. It's a tool that we started to develop, I think in 2018 with a global team in IBM research. And the focus of the tool is really on neural architecture search for various applications. But before I get into the details of that, maybe I'll give you a little bit of zoom out of why we are doing that and all the various areas that my team works in IBM research. So generally speaking, what we deal with is automation of AI. Automation of AI is a very broader concept, but in summary, I think what we are working on are these four quadrants that you see on the screen. On the top one, you see one we call model and dataset lifecycle automation. So people sometimes think about automation of AI just in the term of building a model and deliver this model into an application, but there are a lot more steps to take into account that goes from the data preparation, the way you automate the ingestion of new data, the linking or the cleaning of the data. That also is part of the process. There is, of course, the part of creating the model or tuning model from existing ones. Maybe you want to slightly modify an existing model, but you want to create a completely new model. You have constraints that come from the problem you're solving, and you need, of course, to validate on the test case that are provided. And plus, you have all the part on deployment, on interaction when the model is deployed. So, what the user might trigger meanwhile the model is deployed in terms of interaction, maybe, even the data change over time. So there are a lot of things that require automation. It's not just building the model. Although today what I will focus on is really the modeling part, and all of them, or at least some of them, is what my team focus on in development of automation tools. Then the second block on the right you see is what we call continuous learning to lifelong meta learning, and this is something I will get more in detail through my presentation. But the bottom line idea is that how you build automation for AI, and there is no magic, right? I mean, at the end, AI needs data, and automation of AI as well needs data and metadata. So the idea is you need some sort of system behind that enable you to continuously ingest and store this metadata in an organized way that you can fast query and that you can use to build automation in your tools and in your models. And so this continuous learning system is something that we really develop and is part of one of the core engine behind everything I'm going to show. The last two blocks on the bottom are, maybe seems like less important, but actually they are the most important, because what we actually want to have is that what we do is used by people, so it's used in application. So to make it usable in application, you need two things. You need a nice UI UX, which is not just nice, but is also easy to use, intuitive, and able to expose what you develop in a convenient way. And you need to design for the domain expert that will use it. So it's something that requires also some specific design. And then there is the application. In this case, you see one on civil engineering, but it could be another one. And every application brings its own cases, its own constraints, its own thinking. So it's really not easy to just say, oh, okay, I take an application or whatever, and my things will work out of the box. Sometimes there are things that really need customization. So as I say, today we'll focus maybe in this range. So in the range of the model creation, and I will talk a little bit about this as well. So as I say, NeoNet is the tool I'm talking about, is a tool which really is designed to automate creation of deep learning. I guess everybody in this call is expert or has deep knowledge of deep learning, so I will not spend a lot of time in introduction, but the complexity of this type of models is really the size, the fact that you have a lot of layers, a lot of parameters. So when you want to fully automate the creation of a model, it's something really difficult to do if you want to explore all the possible configuration in a massive exploration. Actually, it makes the problem really impossible to treat in that way. So you need to have some smart techniques that enable you to get to the right model with, the minimum amount of training, the minimum amount of compute resources, and still get very good results. And so that's what we design in terms of NeoNet. So here you see just an overview of, I would say, 5 of the main works that we develop inside this tool. These are all optimizers. So in other words, these are algorithms that enable to find a model, a deep learning model based on some inputs that is the data, some constraints, or maybe time, resources, or other things. And there are 5 different algorithms that we develop over time. They all have their own pros and cons. And in summary, I can tell you there is no method that fits everything perfectly. And there is not a best one, but they have all their space or their area where they work better than others. And that's one of the key things we discover in this world. It's really not possible to find something that really solve all your problem in the same way. There are characteristics of the problem you analyze. It depends really on the constraints that you get from the application that makes it different case by case. And that's why we end up with so many. Now, in this talk, I will focus a little bit on the top 3, just to give you more context around them. Not that the other 2 are less important. It's simply the first 3 maybe are those that we developed first, and we spend more time thinking about some ideas. And the last 2 are maybe in some cases even much better than the previous one, but the ideas that you find the first 3 are kind of embedded also in the last 2. So, and for all of them, there are papers, so you can go and search for all this work and see all the details about that. So the first one I want to present you is one of the first we really developed. It's called Trainless Accuracy Predictor for Architecture Search. We found this nice acronym, TAPAS, which sounds nice because it's, of course, a typical dish in Spain, but it's easy also to memorize. But so this one is one of the first we developed, and I mean, it explains you a little bit our thinking behind automating modeling in AI. So here you see a first layer, which is the offline phase, is what we call learning and teaching our brain, let's say, our lifelong database of experiments. So here we are trying to mimic what a data scientist would do in his life, right? So when he starts, it has no experience about deep learning. It does not know anything about machine learning or models. So he starts from somewhere, right? He starts maybe from a tutorial or from existing models, existing papers, and then he learns through them, right? He takes some of them, run through some data, see how they work, then start to develop his own models, see how they work, and so on and so forth, until he gets to some knowledge that can use to come up with new models, right? And here we are trying to mimic the same process. So we have an offline phase where we have a lot of data sets, which are public data sets. I mean, you can think about Cypher, NIST, and all these data sets, but many others. And what we do is just to generate a lot of models, so a lot of neural networks, train all of them, and measure performance. So we store the accuracy, we store the size, the type of network, the characteristics, the number of epochs that required to train, the hyperparameters, whatever. Everything you can think to store, you store there. And here in the lifelong database of experience, we put all this information. So we kind of memorize this information, and we create this database where we have all these experiments performed in the past that is our knowledge. It's like the knowledge of the software of the data scientist that learns over time. Now that we have this knowledge, we can start to create new models, right? For data that we have never seen. So we get a new data set here. We have never seen this data. We don't know what is inside. And what we do is a phase of characterization of the data, where basically we have, we extract some characteristic of this data. That could be the size of the data, the number of classes if it's a classification data set. It could be the distribution of the classes, the samples that you have. It could be some ranking of difficulty. In this case, in particular, we run a small model on top of all datasets to try to understand the difficulty of this dataset. As you know, for example, NIST and CIFAR-10, they are very similar datasets in terms of numbers of classes and size, but NIST is much easier than CIFAR, right? So there is a difference in difficulty there. And so we enter with these informations that we extract from the new data into our ground truth, and we extract those models, those experiments that we saw in the past that are potentially best fitting, so more similar. Because they were run on similar data. So they seem to perform well on similar data. But instead of doing just simple transfer learning, so we train this model on the new data, we use this information to train a predictor. And this predictor, in a second phase of online phase, it can estimate for us the accuracy of our models without training these models. So we can generate the structure of a lot of different neural network models, combining layers in different ways, and pass this structure without any training to this predictor and get from it the accuracy of the model. And this enables us to do a quick search over a very large space of exploration and identify the potential top models without training them, which makes it very fast. And how fast it is? Well, this is just an idea, a comparison we did 2 years ago with an approach that where each of these gray points here is a trained model. So it's a massive exploration genetic algorithm that starts here with a population of 1,000 models. You see my pointer on the left. And over time, it creates more and more models until it converges somewhere here. You see, you reach very good accuracy. And then the best models are here on the far right. But it takes a lot of time, 10 days approximately, with a lot of resources. So in practical, it's not possible to use this approach because it would cost so much in terms of money and time that is unapplicable. It gets, of course, good results, at least for those time, 2017, these were state-of-the-art results, so it's good results. Now results are better, but just on that time, those type of models were not available. And our approach on the right replicate a similar type of exploration. It's not the same, but it's similar, but fully based on prediction. So it's very fast. It's just a few seconds. You get prediction that is on the same range of the others. And then when you train the top 3 models, you get similar results. Of course, you never get exactly the same. Sometimes this does a little bit better, sometimes a little bit worse. The search space might be slightly different. So it's maybe not even a one-to-one comparison, but it's just to give you an idea that we can get to the same level of results and similar type of approach with much less resources, training only a few models, and basing everything on pre-acquired knowledge. That is the way data scientists work, right? Using his brain or what he learned in the past. And this is an approach that makes it applicable in practice, because then you can afford to spend a few hours training a few models and not days, right? So that's what makes it useful. Now that's one example of what we've done. We have a lot of other methods. I want to show you another 2 at least. I think we have not time to go in detail on everything, but just to give you an idea. A second one is this neurocell-based evolution method. This method is based on this logic that is well described in this slide. So you have a population of models here that can be some state-of-the-art model that you take, for example, ResNet model or other type of model that you can start to put here. And it does a tournament selection, so randomly select some of this model, in this case, the green one from this full pool, compare performance of these models, select only the best one and do a mutation. Mutation is a random. So in this case, we are adding this block here. If you see my pointer, I'm in the bottom corner. And we have this convolutional block. And on the new model that we've created, so this is a mutation of the previous model, we keep training for a few epochs, 1 epoch, 2 epoch, not much, just a little bit. And then we put it back in the pool. So this pool has an additional bullet inside. And the reason why this works is because you have a random selection of models, so not always the same model evolve. These models that are selected, only the best one is trained and only for a few epochs. So it's a sort of intermediate approach, if you want, in terms of computational complexity between the two we saw before. It does not train every model till the end. It trains only the best one, only the one that mutate toward the right direction. The one that mutate in the wrong direction, they will not be selected because they will not win this comparison here when they are selected with other models, so they will not evolve. So it really selects only the best model to evolve, and it does it in a very robust, reliable way because the value you measure here is really the measurement, is really the actual accuracy of these models. And over time, this can lead to better results, a little bit more expensive. You can do a lot of mutation. This is just a slide to show a little bit, but I will not spend too much time here. Maybe I spend a little bit more time to explain another one, just to give you a third flavor of these approaches. This was designed for IoT application. And the idea is to optimize for models that you want to develop for IoT device. And when we did that, there was not yet so many models for, mobile architecture. It was starting in that time. So it was one of the first paper in that direction. And the first thing you realize is that if you have an algorithm that sample model in a space which is near to state-of-the-art space, you will always sample in a region which is far from your design point. Your design point maybe is a region where you have a very small memory in the board. So it's here. And if you sample around state-of-the-art model, you will sample a lot of points here, which doesn't make any sense. So the first thing you need to be careful is to sample in the region near the design point that you want to have. So certain memory that you want to have, certain latency characteristic, and so on and so forth. And second, you need a way to automatically explore this with constraints. So keeping in account the memory that you have, the latency that you want to achieve. And we develop an algorithm which is similar to the others, but takes into account these constraints and the sampling mechanism that I described in the previous slide. So it's able to automatically sample model in the right space. And just to show you some results, so this is a plot of memory versus accuracy. And you see here, we have like the state-of-the-art model. So these are, the popular ResNet model and so other like this, right? So it's all in this top right corner, so very good accuracy, but at the same time, expensive in terms of memory. And when you go down with memory, they lose accuracy. So if you want to optimize for this space here, you can try to get some other models, maybe custom model designed for these birds in fixed point precision. But, it's difficult to come up manually with good architecture. It requires a lot of trials and error. And you can further extend this. We did with other models. You get, some better results, but nothing, let's say, that you can systematically apply. And you have a lot of spaces where you have not sampled any point. So with the approach that I described, you can have a much finer grain exploration of the space. In this case, we explore everything just because we want to show the characteristic of the model, of the method, sorry. But in principle, you can tune the algorithm to optimize in this area or in this area, depends what is your target memory footprint. And you can get significantly better. But additionally to that, you can impose other constraints. For example, you can say, I want to develop this for a board that supports lower precision, even lower than the traditional single precision that you have on GPUs or the half precision. And if you do that, you can move your Pareto line further left or top and get much better points, design points for such kind of models. So in this case, you see, for example, if I am in the space of 10,000 size for the memory, I could arrive to have a model which is still very accurate, while before I was only something around 60% accurate with the same memory footprint. So I can really boost this up a lot by using lower precision architectures that may not be supported on traditional computer, but for IoT device could be specifically designed for that. So this enables really to automate all the space without the person to work on it, and makes a lot of sense in that direction. So in the last 5 minutes, maybe I'll just show you how you can apply this to various applications. Focus, for example, on text. There are some customization that we apply for text, tabular data, or images, depending on what is the application. In this case, for text, what the search is typically oriented to do is either to search for model based on CNN type of layers, which are more compact and cheaper to use and search, or to more complex models like based on BERT. And the reason we have both is because it's not always BERT is better than the others. It depends on the data set you have to do. In some cases, BERT is very expensive for very small accuracy improvement because the sentences are very short and there is no really need for this complex logic that is behind the transformers. While, of course, for longer sentences, it makes a lot of sense to use it. And in this case, you see, for example, for a data set which is relatively big, the time that you get moving from a CNN type GLOVE model to a BERT model is a lot, is like, order of 15 minutes to 2 hours and a half. The accuracy you get is only 1%. So it's questionable in this case if it would really make sense to have the search focusing on BERT type of models while you can get very similar performance with other models. But in other cases, the difference is massive. Maybe not on popular data set. Well, in this case, for example, it was massive, but the time is similar. But we have cases where big data set we saw much better results with BERT than with other type of models. It's always good to have in the search all these options because you never know really what would work better than others. And of course, we have worked to customize this for other languages. We focus for now on Latin type of languages, so German, for example, it could be French, or it could be Spanish. We have not yet generalized to more different use cases like Chinese or other languages. But in principle, it can be done. And the difference is mostly in the preparation of the data. For example, German has some type of words and symbols and accents that are not present in other European languages. Once you account for those in pre-processing, the rest is really very similar. It's really the same, and it can be applied to any language. I spent maybe last 2 minutes on tabular data. So tabular data is another case we worked a lot. What you see here is a comparison between what NeoNet does versus traditional machine learning on benchmarks that were designed for the traditional machine learning. So it's a very unfair comparison because those benchmarks are small data set where we know that ML does great. And we try to use deep learning there to see how much better we could do. And we could do much better. With neural architecture search, we could do much better. And we win 2 times over 3, and in this very unfair benchmark for NeoNet. But when we move to cases where you have a more difficult data set like this one, this Torino data set is just an acronym, Torino, for a data set that gave us from an European project. This data is much more complex. And in this case, we saw that with NAS, we could not only do better than what this machine learning algorithm does, but better also than several competitors and commercial platform as well. Because what we do with this NAS algorithm is really find a good optimized architecture over a lot of possible candidate application architectures. And this year boosts really by 10%, right? The accuracy, almost 10%. 8% versus really the best one we were able to get even manually. So when the data set get complex is where NeoNets win. And the other reason why NeoNets win in many cases is because it doesn't require any data preparation, because machine learning algorithm requires a lot of this feature engineering that is very complex to do, custom to the data. And neural networks, they don't need too much of this, right? I mean, you can do something, but in principle, neural network will learn automatically what are the features that make the difference. And so this is another winning scenarios. And we did some focus on large tabular data in particular, I mean, this is just a list of modification in the code we did, but just to give you an idea, we can do a full neural architecture search over a very large tabular data of 109 gigabytes with 28 gigabytes of text in just 5 minutes. In just 5 minutes, end to end, everything included. If we only account for the training is 3 minutes, but if you account for everything else, it's 5 minutes. When we have one GPU, when we have only CPUs, it's 15, 16 minutes. So it's really reasonable in terms of time, even on large tabular data. And this due to all the tricks that we implemented in the code, and it makes it really usable. So I think my time is almost over. I wanted to leave maybe a couple of minutes for questions, but yeah, I mean, if you want to learn more, you can contact me or any of the colleagues that helped me to develop all this work. And yeah, I hope you like the presentation, and I'm here for questions.